everyone. I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to have a discussion on regulation of alternator using synchronous impedance method. So, first, what do you mean by regulation? Regulation of alternator. So, see the definition first. Regulation of alternator or synchronous generator. Alternator, another name is synchronous generator, that means AC generator with constant speed. Constant speed means Ns equals to 120 F by P is defined as rising terminal voltage when it is load decreased from full load to the full load rated value to the zero. This is known as regulation. So regulation formula E minus V by divided by V. This is per unit regulation. Now if you want the percentage regulation equals to E minus V by V into 100. This is the percentage regulation, and per unit regulation there is no 100. Percentage regulation equals E minus V divided by V into 100. Here E is the no load voltage and V is the load voltage, terminal voltage. Now here the voltage regulation of alternator. In another way we can define as this percentage regulation of alternator in terminal voltage from no load to full load. This is no load to full load rated value divided by full load value. This is full load. E is the no load voltage and V is the full load voltage. Okay, na? From the no load to full load rated value divided by full load rated voltage is known as the regulation of voltage regulation of alternator. Now here we can calculate this regulation of alternator in three methods. First one is synchronous impedance method. This method is also known as the EMF method, and second one is the ampere turn method, that one is MMF method, and third one is the zero power factor method, that is Portier method. So there are three methods to calculate the voltage regulation. First method is the EMF method, second one is the MMF method, and third one is the Portier method. So that is synchronous impedance method, ampere turn method, and zero power factor method. So in your syllabus we have only synchronous impedance method, so that we will discuss synchronous impedance method only. I will explain in this lecture. In your syllabus also we have only one method. So remaining two methods no need to discuss in this module. So now here synchronous impedance method. So in the synchronous impedance method, so first, for calculating percentage regulation, voltage regulation in the synchronous impedance method, so we need three parameters. So first one is the first it is also EMF method. So already we explained. So this method is based on the concept of replacing the effect of armature reaction with imaginary reactance. So this is important. So with replacing the effect of armature reaction, so there is a imaginary reactance. Now here this method is not accurate, so it will give the higher than value from horizon. It will give the higher value. So from the original value it will give the extra value. So for that reason we can calculate as a pessimistic method, because it will give the more than actual value. So that is important. Now for calculating the regulation of alternator, so we need three parameters. So first one is the armature resistance per phase. This is important. This is first one. And second one, open circuit characteristics. From this we can draw the open circuit characteristics can be field current versus EMF, no load EMF, and short circuit current characteristics. So E versus and IF open circuit characteristics from this, and next short circuit current ISH versus IF. This is IF. So this is 3. So for getting in the synchronous impedance method for calculating the voltage regulation of alternator, so we need 3 parameters. We have to conduct 3 tests. Armature resistance D. Here from this we need armature resistance per phase, and after that open circuit characteristics means and short circuit characteristics we need. So to get these 3 parameters, 3 requirements. So first, here this is a voltage regulation formula. So first E minus V by V into 100 for this is for unit, and so E equals to this, E equals to V plus this is full load voltage plus IA, this is armature resistance plus RA plus JXS. Now here XS is can be calculated from the ZS square minus this is impedance and this is the resistance. So this ZS can be calculated from the open circuit voltage by short circuit current. So that after that this resistance is RA, then X can be calculated. This is the armature resistance for phase is this one, and ZS equals to open circuit voltage divided by short circuit current from the open circuit characteristics and short circuit characteristics. After that you can calculate the XS. XS is here, RA is from here, and voltage is full load voltage, and EA is the Thevenin open circuit voltage. So from this we can calculate the percentage regulation of alternator. Now here synchronous impedance method, in this we will conduct 3 tests: open circuit DC resistance test, open circuit test, and short circuit test. From this we can calculate the armature resistance per phase. RA per phase we will calculate. From the open circuit test we will get the open circuit characteristics, that means EMF per IF versus IF field current, and this is short circuit current for and IF field current. Now here first DC resistance test, first one DC resistance test. Here this is the circuit diagram to conduct the DC resistance test. First this is the field winding. So this is a rotor, we will give field winding. This is the rotor and this is the armature. So this is the RYB, it is in star connected output. RYB, this is the field winding. So if you give the field winding, so this rotor excited and this rotating magnetic field will be developed, and this rotating magnetic field cuts the armature conductor and induced EMF will be developed in the armature conductor. That output is here 3-phase supply. So that winding is star connected, means that is star connection RA, and this is the field winding plus and minus. Now here see this in this. So first one is the alternator is star connected. This is star connected with the DC field winding is open circuited. Next point, and it measures the DC resistance between any pair of the terminals. So first here any pair of the first pair of the terminal is I am taking, this is A, R, Y, B I am taking. For R and B I am taking first here any pair of the terminal by using ammeter voltmeter method, or you can use Wheaton bridge method also. Here I am using the ammeter voltmeter method. In place of ammeter voltmeter method, you can use Wheaton bridge method also. First ammeter voltmeter method, connect one ammeter in series with the one winding in series with one phase, that is R phase, and voltmeter is connected across the any pair of the terminals. Here I am selecting R and B. So in between R and B terminal I connected here voltmeter. Now this is the rheostat and DC supply I am given. Now here next step, average of the set of resistors. From this you can calculate the first resistance resistance of RB is the R1. Next second case resistance of RBY. RBY means this is the case. So this is the one, and here this wire is connected here. Don't connect here. Now in that case that is R2. Next RYR, that is the R3. So now average of all three set of resistance, that means R is taken. So R1 plus R2 plus R3 divided by 3 is the RT. So now this is RT. Now next case, RT is divided by 2. So that is DC resistance per phase. So in this way we'll calculate the DC resistance per phase is calculated. If you do this divided by 2, you will get the DC resistance per phase. Next case, while performing this test, alternator should be at rest position, and because effective AC resistance is larger than effective DC resistance due to skin effect. Because of this skin effect, so DC resistance is larger than AC resistance. Means AC resistance is greater than DC resistance, or DC resistance is less than or effective AC resistance, because of this skin effect only. In this case, alternator should be at rest position. So while calculating this DC resistance test, next case, therefore effective AC resistance of R resistance per phase is obtained by multiplying. So this in between you can multiply with. So after that, so I am taking this one 1.25 value. So 1.25 is the correct value. So this one I am multiplying with to get this. So this is the AC effective AC resistance per phase, this one. So if you multiply with this 1.25, then you will get the DC resistance per phase. So now next case, open circuit test. Open circuit test is between induced EMF versus field current. So see the diagram first. So now alternator construction, this is the rotor stator. From the stator we can collect the induced EMF. There is no load, so open circuit test can be conducted without load. So here three loads, three voltmeters I connected here. So this is V1, V2 and V3. So this is R, Y, B and 3 windings. So this is the stator R, Y, B, R, Y and B. This R, Y, B winding is connected in star connection. So R in between R and Y, V1 is connected, in between Y and B, V2 is connected, in between next one this R and B is connected. This is 2 and this is 3. 2. Now 3 voltmeters are connected, because if you see this 3 meter readings, that is open circuit voltage across these terminals, and this is the field winding. This is the field winding. So field winding is given across. This is rotor circuit. Now here field winding current. We need field current and induced EMF. That is the reason we connected this A and this here. This V voltage and this field current versus we are drawing the graph. Now here the DC supply. This is DC supply. Now here open circuit test. So first, in the open circuit test, for determining the synchronous impedance we need. So for determining the synchronous impedance method, alternator running at rated speed and load terminals are kept open. Alternator is running at rated speed, means see here the diagram. So here this load terminals, this is the load terminals R, Y and B are open circuited and connected 1 voltmeter, connected 3 voltmeter across these terminals, and rated speed is Ns equals to 120 F by P, and next running at rated speed, and next case, this means load terminals are disconnected. There is no load terminals are disconnected and field winding is set to 0 value. So this is at 0 value. Now next case, after setting field current 0 and field current is gradually increased step by step. How we will increase the field current? By rheostat. There is a rheostat setup by increasing or decreasing. So by increasing, here you can increasing the rheostat setup. So here you can change this current value. So change this current step by step, and the terminal voltage is measured at each step. So at each step, so here if you take the values from here. This is the field current and this is the induced EMF without load, in no load EMF, and will gradually increase field current. And ET means no load terminal voltage is measured at each step. At each step you calculate it measure, and excitation current is may be increased 25% more than rated. If suppose this rated voltage is rated current is IF, so 25% more than rated voltage. 20, if suppose this rated voltage is 415 volts, 25% rated voltage more than, so then excitation current may be increased. Now here, so draw the graph between open circuit voltage, open circuit phase voltage here. So this is line voltage. So from the line voltage we can calculate the phase voltage. EL equals to root 3 V phase. So now here V phase equals to EL by root 3. This is line voltage and this is phase voltage. And we have field current. Field current can be measured from this ammeter, and EL can be, line voltage can be calculated from the, can be measured from this 3 voltmeters, and from this phase voltage you can calculate. Now the curve is can be obtained. So that curve is known as the open circuit characteristics, and that shape is same as the magnetization curve in case of DC generator. Magnetization characteristic, same as magnetization characteristic, it looks like this. In the next slide I will show you how it will draw. This is the open circuit characteristic, this is air gap line, this is open circuit voltage, and this is field current. So now this is regarding open circuit test. So from the open circuit test, now next short circuit test. Short circuit test, same thing, but here in place of IA armature current with load, with short circuit load terminals are short circuited versus field current. Now here, so see the diagram first. Here this is the diagram, but in case of in the previous case there is a voltmeter across here and voltmeter across here, and there is a voltmeter across here, but here that is open circuit, but here 3 terminals are short circuited. 3 terminals are short circuited. And one thing, how we will measure this short circuit current? So by connecting ammeter in series with this phase, in series with this phase, in series with this phase. Now this is the case here, this one. Now here this ammeter reading, this ammeter reading, and this ammeter reading. This is the short circuit condition. That is the reason we can call this test as a short circuit current. So short circuit current, this one. And next this is short circuit current and field current, same thing. As we see in the open circuit test, same setup here, but here only the difference is replace this voltmeters with ammeters, and it is short circuited. All second ends are connected in to one. This is star and this is the field winding, rotor setup and stator setup. Now see the short circuit test, armature terminals are short circuited through the ammeters. In case of open circuit test, ammeters, armature terminals are open circuited and that are connected across the voltmeters are connected across the armature winding terminals. And next, field winding is same thing here. So field winding first is to be decreased to 0. And before starting the alternator, before starting this alternator, field winding current, field current should be decreased to 0. First it should be decreased to 0, but ensure that first. And next, each alternator should have a range greater than the rated full load value. Alternator is run then run at synchronous speed. So synchronous speed is equals to 120 F by P. Next case, as same as in open circuit test, the field current is increased gradually step by step. So here increase the field current, increasing field current, and after that measure this armature current. These are the armature terminal, that means measure armature current means that means short circuit current at each step of field current, at each step of field current. Next case, up to what time? Up to 150 armature current setup, 150% of rated value, 150% of rated value, field current is increased to get the armature current up to 150 of rated current. In case of open circuit test, 25% of rated voltage value, armature voltage value. Now here the value of field current IF and average of a meter readings at each step is taken. Now here the average of the field current IF, this field current, and average of 3 ammeter readings. So that is the final value. Now a graph can be plotted, and that graph should be straight line passing through. This is the IF and this is the ISS, that is IA. So that diagram is, it looks like this. So this is IF and this is armature current, this is short circuit current. If you draw the graph between these two, if you conduct the short circuit test for alternator at synchronous speed, so that graph should be straight line passing through, or this is the short circuit characteristics. Now here from the DC resistance test, short circuit test and open circuit test, you can calculate the impedance value. So impedance, ZS value, ZS, how you will calculate the ZS? So now if you see the calculation of synchronous impedance, how you will calculate the synchronous impedance method? So synchronous impedance method can be calculated from the open circuit characteristics and short circuit characteristics. Open circuit characteristics on the same graph. So first open circuit characteristics can be drawn from the open circuit voltage and field current, and short circuit characteristics can be drawn from the short circuit current and short circuit current and field current. Now here, so the steps, what are the steps here? The open circuit characteristics and short circuit characteristics are drawn on the same curve. Next point, determine the value of short circuit current and it gives the rated alternator per phase. Determine the value of short circuit current IS, which gives the rated. So at this point here, so determine the value of short circuit current, and it gives the rated alternator. First rated alternator voltage, it is this one, and so draw the horizontal line, and here draw the vertical line from this point, and if it touches this point, this is the rated short circuit current. So now the value, determine the value of short circuit current and gives the rated alternator voltage per phase. And synchronous impedance then we will equals to open circuit voltage divided by short circuit. This open circuit voltage divided by this short circuit. Here this is A, B is the open circuit voltage and AC is the short circuit current. This is the short circuit current and this is the open circuit voltage, and this means AB. Now here OA is the field current OA, this is the field current OA, and this one, and next it produces the rated voltage per phase according to the field. When open circuit voltage is this one AB. Next, this AB by AC, this is the impedance. Z equals to impedance equals to voltage divided by current. Here voltage is the open circuit voltage and current is the short circuit current. Open circuit voltage is this one and current is this one. So because this is the point, so here at rated voltage, this is the open circuit voltage, at rated alternating voltage per phase, that is the short circuit current, this point. This is important, and this AB divided by and AC is known as the impedance. From this characteristics you can determine synchronous impedance. So in this way we can calculate the synchronous impedance. After getting synchronous impedance, you can calculate. So here this RA can be determined from the DC resistance test. So that is first test, and second test open circuit test, and third test is short circuit test. From the open circuit test and short circuit test, ZS is determined. After that, after calculation of ZS, you can determine the XS. Z equals to R plus JX. So Z square equals to R square plus X square. So from this is the formula. X equals to square root of Z square minus R square. Now here what are the assumptions? If you know the Z value, X value, then you can determine easily the voltage. E equals to V plus IA RA plus IA XS. So now RA we know, IA we know, and XA and voltage and this one. So E minus V we can calculate from this, and then you can determine the what are the assumptions. So these are the assumptions. So synchronous impedance must be constant. This ZS must be constant, and next under the flux under this test conditions are same. Under the load conditions also, test conditions and load condition that must be same, flux should be, and effect of armature reaction can be replaced by reaction flux. That flux is replaced by voltage drop proportional to the armature flux, and that armature reaction voltage drop is added to the armature voltage drop. Now here the magnetic reluctance in the armature flux is constant regardless of power factor. Next, let us take one problem. A 400 volts 35 kVA single phase alternator has an effective armature resistance 0.3 ohms, an excitation current of 15 amps, and produces 250 ampere armature current on short circuit, and an EMF of 380 volts and open circuit voltage, and calculate the synchronous impedance and synchronous reactance, means ZS and XS we need to determine. Now here the solution for this and given data here. Now here open circuit ZS can be calculated from the open circuit voltage and short circuit current. That open circuit voltage is this one VOC, and this one is the short circuit current ISC. This VOC can be this one EMF on open circuit test, and this is the short circuit current, this one 250. 380 by 250 is known as, this is the ohms 1.5. And next XS can be calculated ZS, and this is the RA value is this one. This is the armature DC from the DC resistance test 0.3 ohms. Now this is the 1.49 ohms. I hope all these concepts are clear to you. If you have any doubts, you can comment in the comment section below. I will answer to your queries. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.